Good morning, class. Right now we will try to derive a very important tool in transmission line problems at RF frequencies, and that is the Smith chart. We'll introduce the Smith chart, then we will derive the actual Smith chart itself. Thank you. Now, many of the computations required to solve transmission line problems involve the use of rather complicated equations, and we've seen them before. To simplify their solutions, a graphic method of arriving at quick answers is necessary. The most popular graphic chart, the Smith chart, was developed by Philip Smith in 1939 at the Bell Telephone Laboratories in the US. The Smith chart provides a very useful way of visualizing transmission line phenomena. The real utility of the Smith chart lies in the fact that it can be used to convert from reflection coefficients to normalize impedances or admittances and vice versa, using the impedance circles printed on the chart. We'll now go ahead and derive this very important tool. Now, when we start the derivation of the Smith chart, let us consider the reflection coefficient at the load for a transmission line, which is given by gamma L is equal to ZL minus Z naught over ZL plus Z naught. Now, gamma L generally is complex, so it has a magnitude and an angle theta, but we can also rewrite gamma L as having a real part and an imaginary part, as shown in equation 76, where gamma R is the real part and gamma I is the imaginary part of gamma L. Now, the magnitude of the reflection coefficient is always less or equal to 1 by definition, because you cannot reflect anything higher than what has been transmitted. So the reflected wave magnitude is always less or equal to the incident wave. And therefore the envelope of gamma L must lie within or on the unity circle, which means magnitude of gamma L is less or equal to 1. Now, the reflection coefficient at a distance d from the load is given by equation 77, where gamma d is of course generally gamma L e to the minus 2 alpha d, where not alpha d, 2 gamma d, where gamma is alpha plus j beta, and therefore you have the magnitude of gamma L e to the minus 2 alpha d e to the j into theta minus 2 beta d. Remember, the assumption here is that alpha is not 0. But in general, when we are deriving the Smith chart, we assume that alpha is 0, that is, the line is lossless. Now, the normalized impedance is given by Z over Z naught, where Z naught is the characteristic impedance of the line, which is given by 1 plus gamma L e to the minus 2 gamma d over 1 minus gamma L e to the minus 2 gamma d, as shown in equation 78. Now, at d equal to 0, which means right at the load, our normalized impedance is simply ZL over Z naught, which is 1 plus gamma L over 1 minus gamma L, and Z, the normalized impedance, is given by small r plus j small x, because Z is in general complex, so it has a real part and an imaginary part, as shown in equation 76. Now, from equation 76, we replace gamma L with gamma r plus j gamma I, as shown in equation 79. Thus, we have our equation 80, and therefore now we combine, we bring together the real part and the imaginary part. The real part, which is small r, is 1 minus gamma r squared minus gamma I squared over, between brackets, 1 minus gamma r squared plus gamma I squared. So that is the real part of the normalized impedance. Now, the imaginary part is given by 2 gamma I over 1 minus gamma r squared between brackets plus gamma I squared. So we have in equations 81a and 81b the values of the expressions for the normalized resistance, load resistance, and the normalized load reactance, respectively. Now, if we let u be equal to gamma sub r and v equal to gamma sub I, we have for equation 81a, our r is 1 minus u squared minus v squared over, between brackets, 1 minus u squared plus v squared. And if you multiply both sides by the denominator, you find r into 1 minus u squared plus rv squared is equal to 1 minus u squared minus v squared, which is equation 82a. And therefore, when we further simplify this, we have r plus 1 between brackets v squared plus r plus 1 between brackets u squared minus 2ur is equal to 1 minus r. Now if you divide both sides by r plus 1, then you end up with v squared plus u squared minus 2 into ur over r plus 1 is equal to 1 minus r over r plus 1, which is equation 82b. Now, let us now complete the squares on the left hand side of 82b so that we get constant resistance circles. Now, to the left we have v squared, and then we have u minus r over r plus 1, everything squared. And if you square that, then you must add to the right r over r plus 1 squared. And that is what we have done there. And therefore, you end up with, if you add 1 minus r over 1 plus r over r plus 1 all squared, that one gives us 1 over r plus 1 all squared. And therefore, you have v squared plus, between brackets, u minus r over r plus 1 all squared is equal to 1 over r plus 1 all squared. Now, this is the equation of a circle. And it's a circle with the radius 1 over r plus 1 and centered at v equal to 0 and u equal to r over r plus 1. So that is what we have in equation 83, where we have now replaced, we've replaced u with gamma r and v with gamma I. So similarly, for the x equation in 81b, we have x equal to 2v over 1 minus u squared plus v squared. And if you multiply both sides by the denominator, you get u squared and divide everything by x. Then you have u squared minus 2u plus v squared minus 2 times v over x is equal to minus 1, as shown in equation 84. Now, so as before, we complete the squares on the left hand side of equation 84 so that we get constant reactance circles. Now, if you look at equation 84 to complete the squares, now u squared, you bring the 1 to the right, you bring it to the left. So you have u squared minus 2u plus 1 between brackets. Then, not in equation 84, we have v squared minus 2 times v over x. Now, for us to complete that square, remember you have to add 1 over x squared to the left and to the right. So that to the left you have v squared minus 2 times v over x, which is what we have there, plus 1 over x squared. Then to the right you also have 1 over x squared. And therefore, you have u minus 1 squared plus v minus 1 over x all squared is equal to 1 over x squared. So again, you have constant equations of a circle with the radius 1 over x and center u equal to 1 and v is equal to 1 over x. So again, you replace u with gamma r, and V with gamma I, and you end up with equation 85. So we have two very important equations. Equation 85 for constant reactance circles and equation 83 for constant resistance circles. These two circles are what we will use to plot the Smith chart. Now we have for the constant resistance circles, we have the circles to the left. Remember, we are in the complex gamma plane. So you have gamma imaginary on the vertical axis and gamma real on the horizontal axis. Now, if you look at the constant resistance circles, let's start with the case where R is equal to 0. Now, when your R is equal to 0, your center will be 1. So it's a circle of radius 1. The radius will be 1 because 1 over R plus 1 is 1 over 1. And if you square that, you get square root, it's 1. And the center is at gamma R is 0 and gamma I is 1. So gamma R will be centered at 0, while gamma I will be centered at 1. Okay, so that is the circle of radius 1, and that corresponds to R equal to 0. What about when R is equal to 1? Now when R is equal to 1, the circle center is at a half. So the radius is a half because it's at a half squared, so it means the radius is a half. The center, you still have gamma R is equal to, if you have a half there, so it will be 2/3, while gamma I is equal to 0. So with gamma I equal to 0 and the other one being given by being at 2/3, then you have the circle corresponding to R equal to 1, and so on. So it goes on and on. When R goes to infinity, which means when you have an open circuit, then gamma I, the radius is 0. Now gamma R also has an infinite, its radius is now, it's centered at gamma R is equal to 1 and gamma I is equal to 0. So right at the right of the circle, that corresponds to R equal to infinity. So we then have those constant resistance circles to the left. Now, when you look at the constant reactance circles, remember X can be either positive or negative. You get positive X when you have an inductive load and negative X when you have a capacitive load. Now the inductive load would be above, for gamma I is positive, and for reactive load gamma I would be negative. So it would be below the straight line passing through the center, the horizontal line passing through the center of the Smith chart. Okay, so when you have X equal to 0, when your X is equal to 0, your radius is infinite. And your gamma R, the center gamma R is at 1, and gamma I is at infinity. So it means you'll have the straight line passing through the center of the Smith chart. That corresponds to X equal to 0. So it means when you have no imaginary part, which means if your impedance is real, then your value will fall along the straight line passing through the center of the Smith chart. Now, what happens when, for example, your X is 1? Now, when X is 1, the center is at 1, the radius is at 1, but the center, the real part is at 1, and the imaginary part is also at 1. Okay, so when you do that, then you end up with your x equal to 1 circle, and then you also have the x equal to 2 circle, and so on until x goes to infinity. When your x is infinite, then your radius is 0, and your center is at gamma I is equal to 0, while gamma r is 1. So it's right at the end of the Smith chart, at the point right at the center, at the end of the Smith chart. So that corresponds to infinite impedance. So there r is equal to 0 and also x equal to 0 corresponds with the same point. Now, of course, when x is negative, then you have to plot your values of x at the bottom, on the lower part of the Smith chart. Thank you. So when you combine the constant resistance plots and the constant reactance plots, then you get the Smith chart with not too much detail as shown in the figure here. Just notice that the straight line corresponds to real impedances, but if you go above the straight line, that corresponds to positive reactance, and when you go below the straight line, it corresponds to negative reactances. When you are at the outermost circle, that corresponds to the real part being equal to 0. So when you are at the circle where r is equal to 0, then the radius, remember, is 1. That's the outermost circle in the Smith chart. And of course, when your x is equal to, when your impedance is infinite, then you are at the point at the end of the straight line on the Smith chart, where the straight line intersects the outermost circle to the right. That corresponds to infinite impedance, while where the straight line intersects the outermost circle to the left, that corresponds to an impedance of 0. So you have 0 plus j0 to the left, while to the right you have infinity plus j infinity. And then in between you have other values of impedance. The figure on this page just gives us a more detailed version of the Smith chart. The previous one was not very detailed because it was simply indicating what the values tend to be. But here is the typical Smith chart, which is fairly detailed, and we will invite you to print a few copies of this so that you can use it in your practice. When you are asked, for example, to get the input impedance or the load impedance, you should be able to determine this on the Smith chart. And in our next class, we will show how to identify impedances, and when we move around the Smith chart, how to get, for example, input impedance when you know the load impedance, and so on. And also how to determine the admittance, the input admittance when you know the input impedance, or the load admittance when you know the load impedance. Remember, the Smith chart can be used either as an impedance chart or it can be used as an admittance chart. Let's briefly state the characteristics of the Smith chart. We've already shown a bit of that in the plots which we had before. First of all, the constant resistance and constant reactance loci form two families of orthogonal circles on the Smith chart. Two families of orthogonal circles on the Smith chart. Now the constant r and constant x circles all pass through the point gamma r equal to 1, gamma I equal to 0, which is at the rightmost portion of the Smith chart. So along the straight line, and then where the outermost circle crosses the straight line to the right, that is gamma r is equal to 1, gamma I equal to 0. So all constant r and constant x circles pass through that point. Now the upper half of the Smith chart represents positive reactance, which means inductive reactance, while the lower half represents negative reactance or capacitive reactance. Now, if you want to use the chart as an admittance chart, the constant resistance circles, become constant conductance circles, while the constant reactance circles become constant susceptance circles, since Y is equal to G plus JB. Now, one other thing that we will show, and you know, we want to state it here, is that if you go around the Smith chart once at constant radius from the center, then that is equivalent to travel a distance of lambda over 2. That is a very, very important piece of information when you are using the Smith chart. Now, the other characteristics are, at a minimum point, the normalized impedance is 1 over VSWR. Of course, we will show how to get a minimum point when you are moving along a transmission line or a slotted line. There's always a minimum point and a maximum point. We'll show how to get the minimum point and therefore the normalized impedance at that particular point on the Smith chart. While at a maximum point, the normalized input impedance is given by VSWR. These are parameters which we should be able to determine for any given load impedance. Now, the normalized impedance or admittance is repeated every half wavelength. Remember, if you go around the Smith chart once at a constant standing wave ratio circle, then that is equal to lambda over 2. And therefore, after that, the impedance starts repeating itself. Of course, the assumption is that you have a lossless line. Because if you have a lossy line, then, of course, the circle starts getting smaller and smaller because it will look like a spiral. Now, since the normalized admittance is the reciprocal of the normalized impedance for a given normalized impedance, the corresponding admittance values are 180 degrees out of phase in the Smith chart. And we will show you how to determine this. Now, the distances in the Smith chart are given in wavelengths towards the generator or in wavelengths towards the load. Because you either move towards the load or you move towards the generator. Indeed, if you have a transmission line, those are the only two directions in which you can move from at a point. You can either move towards the load, which means you move backwards towards the source. You can either move towards the load, which means you move forwards to the terminating impedance, or you move backwards towards the source. So those are the only way, or the source is also the generator. So those are the only ways in which you can move along the Smith chart. So in our next lecture, we'll show how to utilize this chart, some simple examples. Thank you very much.